You probably have some idea what a chemical reaction is, and I bet you could name a number of chemical reactions off the top of your head. A chemical reaction is when you start out with one set of substances, and then there's this transformation, and you end with a different set of substances. What you start with are called your reactants, and what you end with are called your products. There's all sorts of things that might indicate that a chemical reaction has taken place, anything from changes in states of matter, like the evolution of gas, changes in color, the production of odors, changes in temperature, or the production of light or even electricity. All kinds of things might indicate that a chemical reaction has taken place. In this video, we're going to focus on identifying a reaction's type. There's actually a whole slew of different types of chemical reactions, especially if you get into really complex areas such as organic chemistry. However, for the purposes of this video, we're going to focus on just 6 of those reaction types. Those reaction types are single replacement, double replacement, combination, decomposition, combustion, and acid-base. And before we go any further, let's identify the goals of this video. After watching this video, you should be able to identify a reaction's type by comparing its reactants with its products. And you should be able to identify a reaction's products if you know the reaction type. So let's learn how to identify what type of reaction we're working with. Now there's a helpful analogy for trying to conceptualize what the atoms and molecules are doing as a reaction is taking place. And to help us conceptualize this, I'm going to use these plastic children's bath toys. So what's happening in a chemical reaction is that atoms and molecules are rearranging themselves. They are breaking bonds. They're forming new bonds. You have, two partners who break apart, and one of them goes and finds another partner. This presents a really useful analogy that I like to use when thinking about chemical reactions. The particles that are rearranging during a reaction are acting a little bit like dancers on a dance floor. And there's 2 states that these particles can be in at any given moment. They can either be with a partner dancing together, or they can be dancing solo by themselves. So I'm going to use these little toys to sort of illustrate how do the reactants, the dancers at the beginning of the situation, turn into the products, the dancers, once all the rearranging has taken place. Let's learn about single replacement reactions using the analogy of dancers out on the dance floor. In a single replacement reaction, you have a pair of particles who are currently bonded. So this is a pair of dance partners dancing together right now. And then elsewhere out on the dance floor, you have someone dancing solo. This is an atom or a particle that is not currently bonded to these. This solo dancer is often a metal or sometimes a halogen. And what this solo dancer does is he cuts in. He comes in here and he kicks out one of those particles from that bonded group. And now that dancer, who was once in a pair, is now dancing solo. We're going to head into the lab and do a single replacement reaction with iron 3 oxide and aluminum. In this reaction, the iron 3 oxide is the bonded group, the pair of dancers, and the aluminum is the solo dancer who's going to come in and replace one of those dancers. So let's head into the lab and check out that reaction. I'm going to demonstrate a single replacement reaction. In this reaction, I'm going to react aluminum metal with iron oxide. So I have mixed my reactants, my aluminum metal and my iron 3 oxide. And while I light that, I want you to think about what products might result from this reaction. And remember that this is a single replacement reaction. So what products do you think we'll get? And so here we go. All right, you may notice that those products are glowing. That is because what has been produced is iron metal. So this is a really rapid, powerful redox reaction, single replacement reaction between aluminum metal and iron oxide. So in the single replacement reaction we just saw, we had Fe2O3 plus Al, aluminum, and that produced some products. Now, based on the way that a single replacement reaction works, you might have been able to figure out that the products in that reaction were aluminum oxide, its formula would be Al2O3, plus iron. In fact, iron was that glowing, bright orange-yellow goo at the bottom of the beaker. This particular reaction is also tremendously energetic. It puts out a huge amount of heat, enough to liquefy the iron. Now remember, Using our dancers on the dance floor analogy, what's going on here is that we have this pair of particles. We've got the iron, we have the oxide. Over here is the aluminum. When this reaction took place, the aluminum came in, kicked out the iron, and the iron ended up by itself. This is why we had this molten iron in the bottom of the vessel once that reaction had taken place. The iron was actually kicked out of the iron oxide. And if we were to illustrate what the particles were doing in the single replacement reaction, it might look a little bit like this. Here is the iron oxide, and here is the aluminum. When this rearrangement or replacement takes place, the aluminum comes in, kicks out the iron from the iron oxide, the iron is ejected and becomes a solo particle, and this is what our products look like. The balanced reaction would be written like this. So, it's a great example of a single replacement reaction. Let's learn about double replacement reactions. If we use a dancers on the dance floor analogy for understanding double replacement reactions, what we see is this situation. We have two pairs of dance partners. We have this pair, these are two particles that are bonded, and we also have this pair. This is a separate pair of particles which are also bonded. And in a double replacement reaction, one partner from each pair replaces the other. So what we're really seeing is something like this. So all these dance partners are really doing is just swapping, and now you have two new molecules. There's a number of important things to note about identifying a double replacement reaction. One of the most important is that in a double replacement reaction, you always begin with two pairs of molecules. And quite often these molecules contain what are called polyatomic ions. A polyatomic ion is a group of covalently bonded atoms that take on a formal charge. So for instance, nitrate is NO3 with a formal charge of 1-. And when you're showing polyatomic ions in molecular formulas, quite often you will see parentheses. So if you see a whole bunch of polyatomic ions and a whole bunch of parentheses at the start of a reaction, it might be a double replacement reaction. So let's head over to the lab and do a double replacement reaction. I'm going to demonstrate for you a double replacement reaction. In a double replacement reaction, you always begin with two ionic compounds dissolved in a solution, often water. When an ionic compound dissolves in a solution, we call that state of matter aqueous. So in an aqueous solution, you have a mixture of positively charged ions, those are called cations, and negatively charged ions, we call those anions. So in the example that I have here, I have lead nitrate. So I've got my lead, which represents the cation in this example, and the nitrate, which represents the anion in this example. And I'm going to react my lead nitrate with some potassium iodide. Now keeping in mind that this is a double replacement reaction, what products do you think we'll get when this reaction takes place? So let's do this reaction and see what we get. So I'm going to take some of my lead nitrate here, place it in my test tube. Now I'm going to take my potassium iodide and place that in. See what happens. All right, so we see the formation of this beautiful, brilliant yellow precipitate. And keeping in mind that this is a double replacement reaction, there's really only a handful of products that can be. And this reaction demonstrates a pattern that we nearly always see in double replacement reactions. We always begin with two ionic compounds that are in the aqueous state. And then, when those compounds react, the ions that they're made of switch places, right? They kind of swap partners. And very often in the products, we get substances that are not aqueous. So we have a change in state of matter. Often we'll see solids as precipitates. Sometimes we'll see the formation of water, as in an acid-base reaction. Sometimes we'll even see the evolution of gas. So that's our double replacement reaction. So in the double replacement reaction that we just saw in the lab, we took lead nitrate and we reacted that with potassium iodide. What we got was that brilliant yellow precipitate. So if we look at our dancers on the dance floor and think about what all of these particles were doing, over here we had our lead nitrate, over here we've got our potassium iodide, and what happened was the iodide came over here and kicked the nitrate out of the lead, and we ended up with the lead iodide as a product. Which brings us to one more important generalization about if you're trying to identify if a reaction is a double replacement. You might remember I said that in a double replacement reaction, you always begin with aqueous solutions. You have an aqueous dissolved molecule, an aqueous dissolved molecule. When a double replacement reaction occurs, you nearly always have a change in that state of matter. So in this case, we had the production of a solid, that's called a precipitate. You can also have the production of a gas, or you could have the production of a liquid, such as water. The production of this different state molecule actually drives the reaction. It actually pulls the reaction toward the products. Now, if we were to illustrate our reaction we just saw in the lab between lead nitrate and potassium iodide, it might look a little like this. Here we've got our lead nitrate, and here's the potassium iodide. When they react, the iodide kicks the nitrate off of the lead and replaces it to produce lead iodide, and then the other product is the potassium nitrate. Now, the potassium nitrate stayed dissolved in the solution. It was just floating around. So that's a great example of a double replacement reaction. Let's learn about combination reactions. If we use a dancers on the dance floor analogy to understand what's going on with a combination reaction, you might pretty quickly guess what's going on. We start out with two separate substances. Quite often these substances are pure elements, but they don't have to be. And by the end of the reaction, these two substances come together, and they are now dancing as a pair. We're taking different particles, we're adding them together to make something new. We're making a molecule. Let's head over into the lab and take a look at a darn good example of a combination reaction. I'm going to demonstrate for you a combination reaction. We're going to react hydrogen gas with oxygen gas. Hydrogen gas is in the balloon, and surrounding the balloon is oxygen in our atmosphere. And so we are combining H2 with O2. Since this is a combination reaction, what product do you think will be created once this reaction has taken place? Okay, so I'm going to light my meter stick, and here we go. Ready? And there we have the reaction between H2 gas and O2 gas. That's our demonstration of a combination reaction. So in the combination reaction that we just saw, we started out with hydrogen gas in the balloon. And floating around in the atmosphere is oxygen gas. Hydrogen gas takes on the formula of H2. Oxygen gas takes on the formula of O2. When I hit the hydrogen in the balloon with the match, there was a tremendous emission of energy, light, heat, sound, and what was produced was the combination of oxygen and hydrogen together. You might guess what that is. It's water. So when the hydrogen in the balloon and the oxygen in the air rushed to meet each other, they produced water, and all that fire and heat that we observed was water being born. If we were to illustrate this reaction, it might look like this. Here are the hydrogen molecules, and here is an oxygen molecule. The atoms in the hydrogen and oxygen rearrange and form water. So that's a great example of a combination reaction. Let's learn about decomposition reactions. Using a dancers on the dance floor analogy, in a decomposition reaction, you're starting out with two dance partners that are currently dancing together. And over the course of the reaction, these two particles split up. So by the end of the reaction, you have this particle and this particle. They've gone off in their separate ways. Quite often in decomposition reactions, we see a change in state of matter. For instance, you might start with maybe a solid and you heat it up and you knock those particles apart and you produce some gases. Let's head into the lab and perform a decomposition reaction. I'm going to demonstrate for you a decomposition reaction. In this reaction, I'm going to start with some tin chloride. Tin chloride is an ionic compound. It's a salt. And when dissolved in water, salts take on a state of matter called an aqueous state of matter. So I have my aqueous solution of tin chloride, and in this particular reaction, I'm going to dump energy into it. I'm going to supply that energy with a 9-volt battery, which I have secured using red and black electrodes to this petri dish. I've attached pieces of paper clips to the electrodes to increase the surface area, so here comes our tin chloride. So I've added my tin chloride to the solution and I'm supplying energy in the form of that 9-volt battery. And right away you can see something is already happening here. Now, keeping in mind that this is a decomposition reaction, what do you think is happening to the tin chloride in this reaction? What do you think these products are? So this is a pretty dramatic reaction. Out of that tin chloride solution, we have the appearance of this silvery solid. This is pretty astounding. What do you think that silvery solid is? This is a little bit of an unusual decomposition reaction in that one of your products is a solid metal. So, pretty striking example of a beautiful decomposition reaction. Now, in the decomposition reaction that we just saw in the lab, we started out with tin chloride, that's SnCl2. And when I hit it with some electricity, we saw this beautiful metal appear. Now, if you understand how a decomposition reaction works, you might have guessed that that metal was tin. So using our dancers on the dance floor analogy, we had tin and we had chloride, which were bonded together. When we hit the tin chloride with some electricity, the chloride went off and formed a gas. And the tin was left as a metal in that petri dish. It's actually one of my favorite decomposition reactions. If we were to illustrate this reaction, it might look a little bit like this. Here's the tin chloride, and when we hit it with some electricity, it knocks the chloride off of that tin atom. The chloride atoms bond together and escape the solution as chlorine gas, Cl2. What's left is a tin atom. If you're trying to identify a decomposition reaction, the important thing is to recognize that these dancers started off together, and then by the end of the night, they're dancing solo. So, pretty interesting and kind of unusual example of a decomposition reaction. Let's learn about combustion reactions. In a combustion reaction, you always begin with a fuel and an oxidizer, and you also end up with the same kinds of products at the end. What we usually mean by fuel in a combustion reaction is a molecule that contains both carbon and hydrogen. A common example is methane. Methane is the primary component in natural gas. That's what powers your oven or stove when you see those blue flames. Octane is another common fuel that you're probably familiar with. It's the primary component in gasoline. Now, what we mean by oxidizer is any element that rapidly grabs electrons away from the fuel. The oxidizer that we're most familiar with is oxygen, which makes up a significant component of the atmosphere. So very often, combustion reactions are characterized by the reaction between a carbon and hydrogen containing fuel and oxygen gas. So let's head into the lab and observe a combustion reaction. I'm going to demonstrate for you a combustion reaction. In this reaction, I'm going to react isopropanol, also known as rubbing alcohol, with the oxygen in the air. I'm going to initiate this reaction with a lit match, just a small amount of heat. To accomplish this, I have this large glass carboy, which I have just squirted a small amount of isopropanol into, and I've capped it, and I've let the isopropanol vaporize, and so there is now a large amount of isopropanol vapor in this carboy, and it's also excluded a lot of the oxygen. What products do you think will result from this reaction between isopropanol and oxygen? Remember, this is a combustion reaction. Okay, so I'm going to light my match on a yardstick, get that cap off, let's see what happens. You can see why sometimes this is called the jet engine reaction. So we saw that there was a blue flame. I'll say something pretty interesting about that blue flame in just a moment. But other than the flame, what products were created in this reaction? Can't really see anything in here, but there were really two products that were created in this reaction. One of them is actually left inside the carboy. So if I upend the carboy, there's actually quite a lot of a liquid in there. And this liquid is water. Now, if you look at the reactants of the reaction, you might recognize, well, what happened to all that carbon? Well, the carbon atoms showed up in a gas, and that gas was carbon dioxide. So there's a pretty dramatic example of a combustion reaction. So in the lab, we saw that that combustion reaction resulted in the emission of light and heat. That is characteristic of combustion reactions. They're highly exothermic, so they generate a lot of heat and a lot of light. But let's look at the products that we get in a combustion reaction. So to help us understand what's going on with the atoms and molecules in a combustion reaction, I've built our reactants using a molecular modeling kit. Over here, I've built a fuel. This is propane. This is the same stuff that runs your grill. And over here is oxygen gas, O2. That's our oxidizer. Now, what I'm going to show you here is how the bonds in these molecules all rearrange to form new products at the end. In order to do that, we need a bit more oxygen. So I'm going to add some more oxygen molecules. All right, now I have enough oxygen. I've got my fuel, I've got my oxidizer. Let's see what the products of this combustion reaction are. So now we've built our products. I just rearranged the fuel and the oxidizer so that the bonds between the atoms all kind of swapped places. We end up with carbon dioxide and water as products. Now in the reaction that I just did in the lab, I was able to actually tip the carboy up, and you could see all that water draining out of the carboy. That was this product, the water. And we could also hear the carbon dioxide shooting out of the vessel. So here's really common products of a combustion reaction: carbon dioxide and water. So that's a great example of a combustion reaction. Let's learn about acid-base reactions. Now there's all kinds of ways to classify acids and bases. There's Arrhenius acids and bases, there's Bronsted-Lowry acids and bases, there's Lewis acids and bases. For our purposes, we're going to stick with Arrhenius acids and bases. An Arrhenius acid is any compound molecule that when you dissolve it in water, it increases the hydrogen concentration in the water. That's H+. H+ is a positively charged ion. We call it a cation. So a common example would be household vinegar. This molecule has hydrogen right here, and this hydrogen can dissociate from the molecule when it dissolves in water. And so it's this hydrogen floating around in the water that makes something like vinegar an acid. And then there's Arrhenius bases. An Arrhenius base is any compound or molecule that when you dissolve it in water, it increases the hydroxide concentration in the water. Hydroxide's formula is OH. It's what's called a polyatomic ion. It has a formal charge of 1-. A negatively charged ion is called an anion. So a good example is sodium hydroxide. Sodium hydroxide is a compound that has a sodium ion over here and a hydroxide ion over here. When this dissolves in water, the hydroxide ion goes off, dissolves into the water, and increases the hydroxide concentration in the water. So, keeping in mind that this is the definition of acid and base that we're working with, Arrhenius acids and bases, let's head into the lab and do an acid-base reaction. I'm going to demonstrate for you an acid-base reaction. Acid-base reactions come in all kinds of different versions. This particular acid-base reaction is a type of double replacement reaction. And that's usually the case when you're dealing with what's called an Arrhenius acid and an Arrhenius base. So in this acid-base reaction, I've got an Arrhenius acid, that's hydrochloric acid, HCl, and I also have an Arrhenius base, and that is sodium carbonate, more commonly known as baking soda. Now to really illustrate what's going on in this reaction, I'm going to add a little bit of indicator. This indicator is called phenol red, so I'm going to add that to my vessel here. An indicator is a compound that changes color in different pH environments. So the first thing I'm going to do is add my base to this vessel, and we'll see what happens here. So I've added my sodium bicarbonate solution to the indicator, and we can see that it has remained red. So this indicator is a pretty rosy red when it's in a basic solution. So now I'm going to add my hydrochloric acid, HCl. So here we go. I'm going to add my hydrochloric acid. We see a few things going on right away. So you should have noticed two major changes here. Probably the most notable one is that we have a striking color change. The indicator changed from red to this pretty yellow amber. That indicates that the pH changed. That makes sense. We added an acid to a base, so we would expect that solution to change its pH. We also have the evolution of a large amount of gas. So with that in mind, I want you to think about what might have happened in this reaction. What products might have been created in this reaction? So the acid-base reaction we just saw in the lab was a pretty interesting one because it generated carbon dioxide gas as a product. That's not always the case. In fact, it's really not characteristic of acid-base reactions. It's just kind of an interesting one to look at. But that reaction we saw between hydrochloric acid and sodium bicarbonate might look a little bit like this. Over here, we have the hydrochloric acid, and here is our sodium bicarbonate. The hydrochloric acid produces a bunch of H+ ions floating around in the solution, and the sodium bicarbonate produces a bunch of hydroxides floating around in the solution. These hydrogen ions and hydroxide ions find each other in the solution and they produce water. So for a reaction between an Arrhenius acid and an Arrhenius base, you always get water as one of the products. If we look at what's left over in the reaction, we have sodium ions and chloride ions floating around in the water. So one product of an Arrhenius acid-base reaction is also a salt, such as sodium chloride. That's common table salt. The reaction we saw in the lab had carbon dioxide as a byproduct, which actually left the system. That's why we saw the formation of gas, all that fizzing in the Erlenmeyer flask. That fizzing gas was a little bit of a fun bonus in that reaction. So that's a couple of good examples of acid-base reactions with Arrhenius acids and bases. Let's review the goal of the video to make sure that you met it. After watching this video, you should be able to identify a reaction's type by comparing its reactants with its products. And you should be able to identify a reaction's products if you know the reaction type. If you can't do that, go back and watch the parts of the video you didn't understand. Until next time, remember, you can learn anything.